Hi everybody, my name is Rupa, working class assistant professor in Chevron Engineering College in the Department of Electrical and Electronics Engineering. I am dealing the subject renewable energy sources and today's topic is single basin arrangement of tidal power plant. So now we discuss about single basin arrangements. It is the simplest way of tidal generation power. It uses only single basin, that's why the name existing single basin arrangement. So this will be arranged in the following manner once we go through them. First one, a single basin arrangement. There is only one basin. It is interacting with the sea. Okay, one basin is interacting with the sea, and these two are interacted or separated by a barrage. And the flow between this barrage, the flow between this gap, nothing but a basin and the sea. It is through sluiceways. Sluiceways means gates. Okay, so also these sluiceways are also called as sluice gates. So these are located conveniently along the dam. Where we have convenient to place this sluice gates, we are placing this. Okay, so potential head means level, higher level, lower level. This is called as head. Okay, so this potential head, it is provided by rise and fall of the tide water levels. Okay, so the potential heads level, that means low level head and high level head, these are provided by the fall of the tides. Okay, fall and rise of the tides, these potential heads are constructed depending upon the. Okay, so this is usually this this potential head, this is actually accomplished by blocking of the mouth of long, we are having long narrow way. So this suppose if you take a estuary, if you take this long narrow estuary, it is usually accomplished by blocking the mouth of a long narrow of a estuary. Okay, so this is done by a dam across it. This blocking is done by the dam. So if you construct a dam at the estuary, it will be looking as a reservoir. So it completes the reservoirs. So this gap and barrage, this embodies, that means this includes a number of sluice gates. Okay, so this includes number of sluice gates and low head turbine sets, etc. So this generation of power, using this generation of power is achieved by either of these three arrangements. First one is single upcycle system. First one is single upcycle system, and second one is single tide cycle system, and third one is double cycle system. So we can go through these three types of arrangements only in single base arrangement. Okay, so if you go for first one, single upcycle system. So this is a single upcycle system diagram. Okay, see, when the flood tide, that means flood means we are getting large amounts of water. So we can term this flood tide as high tide. Okay, so in the technical terms, we are calling this high tide as flood tide, FLOOD, flood tide. Okay, so this, when this high tides comes, the sluice gates are opened. Okay, so when the flood tides comes, sluice gates are opened. If you open the sluice gates, this is the mediating between the water and the sea, right? Water, sea and the turbines. So if the high tide comes, we will open the sluice gates and we will permit the sea water to enter into the basin what we have constructed. Okay, so we can call it as basin or reservoir, both. Okay, so when a high tide comes, we are opening the sluice gates and we are allowing the water to flow into the basin. Okay, so at this time, the turbines are shut. That means not worked. Okay, so at the time of opening the sluice gates and allowing the seawater to occupy the basin, we are shutting off the turbines. So turbines are not run. We are not allowing any water to fall on the turbine. Okay, so now if you open the sluice gates and allow the water to occupy the basin, the reservoir starts filling with water, right? And the level will be rising. So till the maximum tide level is reached, we are doing this. Okay, so until the maximum tide level is reached in the reservoir, we are allowing the water. Okay, so at the beginning of the ebb tide means nothing but, ebbing means flowing back of tide, nothing but. Ebb tide means flow back of tide. So at the beginning of the flow back of tide, the sluice gates are closed. Okay, so when the tides move backwards, the sluice gates are now closed because the reservoir is filled with the maximum limit of water. Now the generation takes place. Okay, so the generation of power takes place after the reservoir is filled to the maximum level. Okay, so when the sea is ebbing means, you know that, flow back. Okay, so when the sea is ebbing, the generation of power will be taking place, and water from the basin, that means water from the reservoir, flows over the turbine into the lower sea level. Okay, suppose if you see this, this is the sluice gate, and we are opening this sluice gate and allowing the seawater to flow into the reservoir, nothing but dam or nothing but basin. Okay, so after the reservoir is filled with maximum limit here, maximum limit of water, now the sluice gate is closed and this water is again flow backed onto the turbine, and generation of power will be produced. Okay, so the basin flows over the turbine into the lower sea level. From this, the water from the basin flows back to the sea levels. So after 2 or 3 hours, after this process is done, after 2 or 3 hours, when there is sufficient difference between the full reservoir level and the falling tide level, then the turbines are run. Okay, so these are the sluice gates here. This is the high tide and this is the reservoir filling. So when there is sufficient difference between the high tide and this reservoir water, then sluice gates are open. So after this process will be taking after 2-3 hours. So generation of power will be produced after the 2-3 hours of process. So now when there is a difference between the full reservoir level and the falling tide level, the turbines will be started and they will be working until rise of the level in the next flow tide, and the falling reservoir level reduces to an effective head on the turbines. So the pressure on the turbines will be more at some point. So up to that point, the turbines will be running. So after the pressure is increased onto the turbines because of high tide levels, next high tide levels, then the turbine will be stopped. And again, sluice gates are open and the water is allowed back to the reservoir filling. So this is the process of single ebb cycle system. Okay, next if you go for second one, so this is the third diagram. We are see, reservoir is emptying here, reservoir is filling by allowing the water to flow in this direction, and if you allow the water to flow onto the turbine and allow the water to the sea level in this direction, this is the ebb tide, that is flow back tide. Okay, so when you allow the reservoir water again to the sea level, the turbine will be running here. Okay, so after emptying reservoir, again it is stopped because this ebb tide, this high tide will have a pressure on the turbine. So the turbine will be stopped. This is single ebb cycle system. Next we will go through single tidal cycle system. So in this single tidal system, the generator is affected when the sea is at flood level, tide. Okay, so the water of the sea, these are admitted into the basin from the turbines. Through the turbines, these seawater are admitted. That means these seawater are allowed to fill in the basin through the turbines. Okay, so as the flood tide, heavy tide, high tide period is over, then the sea level starts falling again. So the generation will be stopped. So the basin is again drained into the sea through the sluiceways. So this flood operation scheme, it needs largest size plants. Okay, so this size plant is needed larger and these are operated for short periods, and as these are operating for short periods, we are having less efficient as compared to the ebb-tide operation. Okay, so this ebb operation plant will be of smaller size, but it will operate with large periods. Okay, so the as long as the period of generation power, at the beginning and finishing of the work, we are having minimum operating head only. Okay, and adjustable blade bulb turbines are used specially for this arrangements, for these operations. These are used under low and variable heads also. Okay, so all these turbines may be reversible, which can work as a pumps after the high tides in order to increase the amount of water in the storage lake until the generation starts. Okay, so this way turbine operation may be prolonged to 10 or more hours. Okay, so we are having 12 hours. Out of 12 hours, we are running the turbines more than 10 to or more than 10 hours. Okay, so this tidal cycle, this type of single tidal cycle system, in this it requires a deeper reservoir. Okay, so we are locating here, we are requiring here deeper means we have to locate the sluice gates as possible as deeper. Okay, so if you are going for a choice of deeper reservoir, this deeper reservoir construction will be of greater constructional cost. Okay, so it is estimated that energy produced by a ebb cycle system, it is as much as 1.5 times than by the tide cycle system. So out of both, ebb cycle system is more efficient than the tide cycle system because it is 1.5 times more than the tidal cycle system. And we will see now the disadvantages now. The main disadvantage in both ebb cycle system and as well as tidal cycle system, it is intermittent nature of this operation. Okay, so the maximum power cannot be reached by using these two types of operations. Only we can go for intermittent nature of their operation. Okay, so these will be these intermissions will be occurring at regular intervals, and so as these are occurring at regular intervals, not always, only some at regular intervals we are getting this intermittent nature of operation. So if you supplement this with the other type of renewable energy source, we can go for a maximum power generations. Okay, so this system can be used to generate power both in the ebb and nothing but flyback and flood tides with the help of single basin only. Okay, so if you generate the power using flood tide, it is called as single basin. And if you generate the power both with ebb tide and flood tide, both, if you use both ebb tide and flood tide for generation, it is called as double cycle system, because during the flood tide only when the water is flowing in one way only into the single basin, we are generating the power. When the water is flowing back, we cannot run the turbine there. So if you run the turbine in both the cases, when the water is flowing into the reservoir and back to the sea level, in both cases, if you are able to generate the power by using the turbines, then it is called as double cycle system. Okay. So this is a double cycle system. See here, when the seawater is flowing into the tidal basin, we can run the turbine, turbo generator here. Again, when the water is from tidal basin, ebb system, this is called as flow back, nothing but ebb system. So when the tidal basin is emptying into the sea level, again in this process, go back process also, we can run the turbine generator here. So that's why it is called as double cycle system. Single cycle system means only this one, A diagram is only applicable. So while the sea is flown out with the water and tidal basin is filling with the water, at that time only we are able to generate the power. So if you can both generate powers in both ways, it is called as double cycle system. Okay, so the direction of flow through the turbines during the ebb and flow tides, these alternates. Okay, so but the machine either it alternates, but the machine will be acting as a turbine for either direction of flow only. Okay, so for either direction of the flow, the turbine will be acting as a generating machines. So in this method, generation of power, it is accomplished by both emptying and filling cycles. So this is filling cycle and this is emptying cycle. Okay, so both filling and emptying process takes place during a short periods of time only. Okay, so this filling is done when the ocean is at high tides and the water is let into the basin at low level tide. Okay, so the emptying is done when the ocean is at low level tide and basin is at high level tide. Okay, so when the ocean is at low level tide and basin is at high level tide, emptying process starts. So this is the filling process and this is the emptying process. So filling process will be start when sea level is higher than the tidal basin. Empty process will be start when the sea level is low than the tidal basins. Okay, so that's why it is called as low tide. That means when compared to the sea, we are talking these names. So when the sea is high, it is called as high tide. When the sea is at low level, it is called as low tides. Okay, so this flow of water will be in both the directions. It is used to drive number of reversible water turbines. So each driving turbine can produce electrical energy. And electrical power will be generated during short periods. Okay, during each tidal period of 12 hours 25 minutes or every 6 hours 12.5 minutes. Okay, so though this double system is of only short duration interruptions in turbine operations, a continuous generation of power is not possible. Okay, so further we can coincide only some occasional periods of peak demand. Okay, so these problems are discussed. Now these problems are discussed. These are the disadvantages. At every time we cannot give continuous demand. Only some occasional times only we can reach the peak demand. So other drawbacks, these are the drawbacks which are overcome in next type of arrangement, that is double basin arrangement. Okay. Next we will see double basin arrangement. See.
We will see the arrangement of double basin type tidal power plant. First one is upper basin and second one is lower basin. We have two basins and two sluice gates. So these sluice gates are used to open, and we are having a turbine in between upper base and lower basin, and seawater will be entering to the upper basin through the sluice gate, and it is moving on to the turbine and the water is entering into the lower basin. So after that, this will be going to the reservoir. The wastewater is allowed to go to the reservoirs. It is called return water. Now we will see the operation from the seawater. When the water enters the upper basin, the sluice gate is open and the water will be filled in the upper basin, and this filled water will be flowing on to the turbine. So the turbine rotates and the wastewater will be flowing on to the lower basin. Okay, so the lower basin will also get filled water, and when we open the sluice gate, the water in the lower basin will be entering to the reservoir, that is the sea level. So this is a return water. This is double basin, upper basin and lower basin.
So see here, once again. So actually it requires two types of adjustment basins. One is called as upper basin and second one is called as, this is also called as, upper basin is also called as high pool. Okay, so the water level is maintained above here. The water level is maintained above than the lower basin here. Okay, so this is always a head between the upper and lower basins. This is always a head. That means it will be at topmost. Electricity can be generated continuous at variable rates through this one. Okay, so in these systems, the turbines are located. See where the turbines are located? The turbines are located between the two adjacent basins, upper basin and lower basin. Why? These sluice gates are usually embodied in the dam. These are embodied at the dam across the mouths of two estuaries. These are the mouths of estuaries, and these sluice gates, two sluice gates are located at the mouth of the estuaries. And at the beginning of the flow tide, heavy tides, these turbines are shut down. These are not worked. Okay, and first, what is happening? The gates of the upper basin are opened here. So when we open the gates of the upper basin, suppose A, this is basin A and this is basin B. Okay, so this is basin A and this is B. Okay, so if you go first at the beginning, these sluice gates are closed and turbines are closed. So now our process starts. First, the sea level is allowed to enter into the upper basin A, and here B basin is closed, right? B basin is closed. It is not allowed to open. So A is open. Okay, upper basin is open. So in this A basin, the water will be filled. Okay, so if the water fills here, there will be a sufficient difference of levels in the A and B basins. Okay, so no water will be there, highest amount of water will be there. So this gives the large amount of difference levels in the upper basin and lower basin. Now the pressure on the turbine will be increasing, and now as soon as the rising water level A are reached to a sufficient difference of head between the two basins, now the turbines are allowed to start. Okay, so the water flows from A to B through the turbines, and the turbines will be connected to the generator and electricity will be developed. So this power generation thus continues stimulously with the filling up the basin A. So at the end of the flood tide, A is full of water and water level is at maximum. Then its sluice gates are closed. After the basin is filled with the maximum level of water, the sluice gates are closed here. So now this is the ebb tide level. Okay, flow back of water. So when the ebb tide level goes lower than the water level in B, here the sluice gates are open. Okay, so here when the turbines are run, the water will be flowing from upper basin to lower basin. So when the ebb tide level gets lower than the water level in B here, okay, then sluice gates are open, whereby the water level in B, which is arising and reducing the operating head, starts falling with the ebb. So here it starts falling with the ebb. So the this will be continuous process until the head and water level in A, it is sufficient to run the turbines. So with the next flow tide of cycle, it repeats itself. So this is the twin basin system. This is longer and more continuous period of generation per day. It is possible. Okay. So the small gaps in the operation of such stations can be filled by the thermal powers. Okay. So if you take complementary with the thermal power station, the small gaps means which we are not able to produce power. Okay, so these are the small gaps which we are not able to give power. Those gaps can be filled by the, or these can be used by the complementary, means additional to the thermal power plants. So this operation of two basin scheme, it can be controlled so that there is continuous water flow from upper to lower basins. Always if you open the sluice gates and allow to run the turbine, it is a continuous process here. This is a continuous cycle. Okay, so this is a continuous cycle. However, the water head between the basins should vary each tidal cycle. Okay, so one way of improving this situation is it is to use of peak power. Okay, so from the tidal power generators, from the alternative system, the to pump water, these have to pump water from the low basin to the high basin. Okay, so if you use additional improvements like this, we can go more effective. Okay, so this is very simple to pump storage system in hydroelectric power stations. Next, we will see the estimation of energy and power in simple single basin tidal system. Okay, so for single basin tidal system, we will estimate the energy and what is the amount of power, actual power generated by a real tide system. Okay, so this expression, this is the basin, this is the area level, and this is the height, and we are considering for small height dh, and this is the high tide level, this is the range r of the high tide level, and this ocean, this is for ocean, this is low tide level, and this is the high tide level, and this is the reversible turbine, and gates are also located here. Okay, so the final expression for maximum energy which is generated during one generation period, it can be derived with the help of this diagram. Okay, so this shows the case of basin beginning at the high tide level and emptying through the turbine to the oceans, which is at low tide level. Okay, so same energy will be generated in reverse process also. The amount of energy will be equal in both the cases, reversible process and normal process. So during the emptying process, means during the emptying process from here to here, from left to right, the differential work done by the water, it is proportional to the potential energy at time. Okay, so if you are considering a tidal range of r and an intermediate head at a given time, suppose we are taking not low and high, we are taking a intermediate head. Okay, so at a given time, sometime the amount of work done is calculated. Actually, the amount of work done is calculated considering a small head dh for an intermediate head h as shown in the figure C. So we can write dW is equal to dm into g into h. Okay, so here where W is equal to capital W will be work done by the water. So it will be expressed in kilocalories or kgs or simply joules. And here G is gravitational constant and mass is M is mass flowing through turbine. It is expressed in kgs. Okay, and small h it is the head M. Okay, and here next equation, but we know that actually dW work done is equal to dm into G into h, but we know that we can write dm is equal to minus rho a dh. So if you substitute this dm value here, we will get the final total expression dW is equal to dm value minus rho a dh into G into h. So in this rho is called as water density. It is expressed in kgs per meter cube. And here capital A, it is the here A area, basin surface area considered constant per meter square. We are considering this area constant per meter square. We are considering this constant area A. So we have now the work done dW is equal to minus rho A dH G into H. Okay, so from this the theoretical total theoretical work during all the during a full emptying, or suppose we can take filling also during full filling. Okay, so while filling and while emptying, full filling and full emptying, the theoretical work done is integrating the third equation. Third equation means W equation here. This is the third equation. So if you integrate this equation expression, we will get W is equal to from limits R to 0. Range from R to 0 dW, that is equal to minus G rho A limits. These are the constants. So we are keeping aside from limits R to 0 H dH. Okay. So this will become H by 2 H and this 1 will be there by divided by H. So those will be cancelled and remaining we are getting R square minus 1 by 2 R square. So minus minus gets cancelled. And remaining 1 by 2 will be there. G into rho into A into R. In the place of R, sorry, H, R. Okay, so here R square should be there after integration. Okay, minus 1 by 2 we will get minus 1 by 2 R square. So minus minus gets cancelled, R square will be remaining. So next, here the work is, if you observe this equation, the work is proportional to square of the tidal range. Okay, so W here is proportional to the square of the tidal range, and the power is the rate of doing work. Okay, power is the rate of doing work. Already we know this definition. So now we will obtain the average theoretical power in watts. So before that we have to see one point. So this power is generated during, what is the power? This is the power generated during emptying or filling. Okay, and no power is generated during the rest of the time. So the average, so once the power will be maximum and other time the power will be minimum. So the average theoretical power, it is derived by the water, in the water is W. When we divide this W with the total time it takes each field to repeat itself, we will get the theoretical power. So for this the work done, the time is 6 hours or 12.5 minutes as shown in before figures. Okay, so 6 hours 12.5 minutes can be written as 22350 seconds. Okay, 6 hours or 12.5 minutes can be written as 22,350 seconds. So thus average theoretical power in watts is work done by time. So time means it is the time which takes for each period to repeat itself. So for every 6 hours, 12.5 minutes, this cycle will be repeating. Okay, so the time can be calculated as 6 hours 12.5 minutes. So 6 hours 12.5 minutes can be converted into seconds as 22,350. So the time is work done by time, W by 2 into this time. So we are having two cycles here. So 2 into 22,350. So work done W is equal to, sorry, here we are taking for only one cycle, not two cycles. After that we will calculate overall power for two cycles. That means in a day. So we are taking this for a half day, only 6 hours. Actually 12 hours will be there. We are taking only for 6 hours. So here W is 1 by 2 0 A R square and time is 22,350 seconds. That is equal to 1 by 44,700 G rho A R square.